Every DNS lookup begins with a compact block of just 12 bytes. Those bytes identify the conversation, tell us whether the message is a query or a response, request recursion, report errors, and count the records that follow. If you can decode this header, a DNS packet stops looking like random hexadecimal data and starts reading like a structured message. In this lesson, we will decode every field, then verify what we learned against a real packet capture of a live lookup for KnowDDI.com. Before zooming into the header, place it inside the complete DNS message. The header is always first. It is followed by 4 logical sections: question, answer, authority, and additional. The question states what the client wants. The answer carries records that directly answer it. Authority records identify authoritative information, and additional records carry supporting data. Not every section contains records in every message, but the header is always present. One important distinction: QNAME, QTYPE, and QCLASS are part of the question section. They are not fields inside the 12-byte header. The 12-byte header contains 6 16-bit words. The first 2 bytes hold the transaction ID. The next 2 form a dense flags word. The final 8 bytes are 4 counters: QDCOUNT, ANCOUNT, NSCOUNT, and ARCOUNT. In network byte order, the most significant byte arrives first. That means the captured query header, A0F0, 0120, 0001, followed by 3 0 counts and a final count of 1, can be divided cleanly into these 6 words. The transaction ID is a 16-bit value chosen by the program that creates the query. The server copies it into the corresponding response. A client can have several DNS questions in flight, so the ID helps it match each reply to the correct request. In our real capture, the query uses 0xA0F0. The response returns the same value. The ID is useful for correlation, but it is not an identity, a session, or a security guarantee. Modern resolvers also use source port randomization and other defenses, because a 16-bit value alone is far too small to establish trust. The 16-bit flags word is where the header becomes especially expressive. QR is 1 bit, 0 for a query, and 1 for a response. OPCODE is 4 bits and describes the operation. Ordinary lookups use standard query, value 0. AA means authoritative answer. It is meaningful in a response and tells us the responding server is authoritative for the name involved. TC means truncated. When a response does not fit the available transport size, a client can retry using a transport that supports a larger message, traditionally TCP. These fields let one glance at the header answer 3 questions. What kind of message is this? Who is speaking? And was the message complete? Next come RD and RA. Recursion desired is set by a client asking a recursive resolver to pursue the answer on its behalf. Recursion available is set in a response when the server supports that service. The original specification reserved the next 3 bits as Z and required them to be 0. Later, DNSSEC standards assigned 2 of that space to AD and CD. Authentic data is used by a validating resolver to indicate that the relevant answer data passed DNSSEC validation. Checking disabled lets a client ask a security-aware resolver not to enforce validation for that query. 1 reserved Z bit remains. These bits are easy to confuse with the DO bit, but DO is not in this header. It lives inside the EDNS opt record. The last 4 bits of the flags word are the response code, or RCODE. 0 is no error, 1 is format error, 2 is server failure, commonly shown as SERVFAIL. 3 is NXDOMAIN, meaning the queried name does not exist in a relevant namespace. 4 is not implemented, and 5 is refused. A no-error response can still contain no answer records, so never interpret RCODE in isolation. Read it together with the section counts and the records. The original 4-bit field supports 16 values. EDNS extends that code space by placing higher-order bits in the OPT record. The remaining 4 header words are counts, not byte lengths. QDCOUNT tells us how many questions follow and is usually 1. ANCOUNT is the number of resource records in the answer section. NSCOUNT is the number in the authority section. ARCOUNT is the number in the additional section. In our query, QDCOUNT is 1. The answer and authority counts are 0, and ARCOUNT is 1. That final one does not mean the query already contains an answer. It means an EDNS opt pseudo-record is present in additional. The counters tell a parser how many structures to expect. Immediately after the header comes the question. QNAME encodes the requested domain as length prefixed labels. KnowDDI.com becomes a label length of 7, the 7 characters KnowDDI, a label length of 3, the characters COM, and a 0-length root label. QTYPE says which kind of data is requested. R-value1 means an A record for an IPv4 address. QCLASS is 1, meaning the internet class IN. Because QNAME is variable length, the complete question is not part of the fixed 12-byte header. Keeping that boundary clear makes manual decoding much easier. Now apply the model to our real Wireshark capture. The client sends a standard query to 1.1.1.1 over UDP port 53. Transaction ID is 0xA0F0. Flags are 0x0120. Query, standard opcode, recursion desired, and the AD awareness bit set. The counters are 1 question, 0 answers, 0 authority records, and 1 additional record. The question asks for the A record of KnowDDI.com. The response arrives about 225 milliseconds later with the same transaction ID. Its flags are 0x8180. Response, recursion desired, recursion available, and no error. The answer count becomes 1. At the time of capture, the returned address is 168.231.74.249 with a 5-minute TTL. The additional section in both packets contains an opt pseudo-record defined by EDNS. It is not cached DNS data. It carries control information for this exchange. The class-shaped field advertises a UDP payload size. The TTL-shaped field carries an extended RCODE, the EDNS version, and flags. The DO flag means DNSSEC OK. The sender can receive DNSSEC security records. Our query advertises a payload size of 4096 and sets DO. The response advertises 1232 and also sets DO. This is why a modern packet lesson must separate the classic 12-byte header from extensions placed elsewhere in the message. When you inspect DNS, read the header as a sentence. Match the transaction ID. Decide whether it is a query or response. Decode the flags. Check the RCODE. Use the 4 counters to understand which sections follow. Then read the question and the records, including any EDNS OPT record. That sequence turns a dense packet into an explainable exchange. For more practical lessons about DNS, DHCP, IP address management, and DDI as a whole, visit KnowDDI.com.